Hello, we are Team 9 consisting of Mark, Jenna, Chris, and your presenter for today, Wally. We will be talking to you about the surface chemistry of textiles. First, a little background about modern day textiles. Textiles are made from weaved organic or synthetic fibers that make up a wide variety of fabrics. This coarse weave produces a porous coarse microstructure as seen in the photo to your right. This structure is responsible for fabric optimal performance in breathability and flexibility, while its large pores and gaps produce poor water resistance and resistance to chemicals and combustion. Surface coatings on textiles are typically used to improve fabric's hydrophobicity, for example, in outdoor clothing as shown in the picture. Ability to resist combustion, improve mechanical integrity and UV protection, and resist chemical penetration and deterioration. In later slides, we will be going over hydrophobicity and flame retardancy in more detail. In order to enhance the properties of textiles, we can manipulate two main properties. First, we can chemically change the composition of fibers. This is difficult as many products have mechanical or financial restrictions making this difficult. Second, we can deposit a surface coating on the fabric itself, allowing for a wide variety of possible property enhancements for a single fabric. To deposit these coatings, there are four main processes. These being chemical vapor deposition, CVD, physical vapor deposition, PVD, atomic layer deposition, ALD, and padding. For the sake of this presentation, we will focus on ALD and its comparison to padding, the most used method in this industry. Padding is the industry standard to deposition of surface coatings and is the most widely used method today. It is typically performed by coating entire sheets of fabric into a solution that has the desired property. Thickness is controlled by the feed rate of the fabric and scrapers or rollers to remove the excess solution. Atomic layer deposition is a thin film deposition technique based on layer by layer chemical deposition. It is a subclass of chemical vapor deposition. However, ALD can achieve more dedicated deposition at a nanoscale of less than 10 nanometers, the thickness of a layer of aluminum oxide. Most ALD processes contain two time-separated half reactions. As the precursor and co-reactant species are transported into the reactor separately, two surface reactions occur, and each of the surface reactions are self-limiting. Then, the two reactions proceed sequentially, eventually depositing an atomic level control film. Looking at the ALD cycle, a typical ALD process is divided into 4 steps. Let's take the synthesis of aluminum oxide from trimethyl aluminum, denoted as TMA, and water as an example. During the TMA exposure, TMA dissociatively chemisorbs on the substrate surface, and any remaining TMA is pumped out of the chamber. The dissociative chemisorption of TMA leaves a surface covered with methyl aluminum. The surface is then exposed to water vapor, which reacts with the methyl group surface, forming methane as a reaction byproduct and resulting in hydroxylated aluminum oxide surface. In 2015, following the typical procedure mentioned before, ALD was used to transform the hydrophobic surface of wool fiber to superhydrophobic with a contact angle of 160 degrees. It is worth mentioning that to avoid issues brought by high temperature, which could trigger a considerable thermal degradation to wool fabrics as protein fibers, they used a relatively low temperature of 80 degrees Celsius. Because of the formation of a strong aluminum-oxygen bond during aluminum oxide ALD, the surface reactions are very efficient and self-limiting so that the aluminum oxide ALD can be deposited at a relatively low temperature available for wool fabrics. After 100 cycles of aluminum oxide coating, a super hydrophobic surface will be obtained, and aluminum oxide nanoparticles on the surface of wool fabrics are observed, as shown in the SEM image on the right side of the slide. Most importantly, the superhydrophobic surface was built after this procedure. The static water contact angle of wool fabrics was about 130 degrees, which is also hydrophobic. However, after aluminum oxide coating, the static water contact angle of ALD coated wool fabrics increased to around 160 degrees, which suggested that ALD coated wool fabrics had a superhydrophobic surface. Interestingly, the durability was evidently enhanced as shown in Figure A. After exposure to atmosphere for 1800 seconds, the static water contact angle of control wool fabrics decreased to almost 0 degrees, and that of ALD coated wool fabrics remained at about 160 degrees as seen in Figure B. Liquid in our daily life was involved in this test, such as orange juice, milk, coffee, tea, and Coca-Cola, as seen in the figure. They all exhibited similar improvement in superhydrophobic properties after aluminum oxide coating by atomic layer deposition was introduced. Here, I would like to discuss why ALD modified wool fabrics exhibited a superhydrophobic surface, what is the relation of this modified surface morphology, and the exhibited superhydrophobic properties. As you can see from the figure on the left, the wetting of 4 different surfaces is shown. As the roughness goes higher, different levels of roughening strategies are employed, from a flat, smooth surface to nanostructural rough surface to microstructural rough surface, and finally to the hierarchical structure, which is exactly the surface structure of lotus leaf that we've talked about before in class. In this example of coating aluminum oxide nanoparticles onto wool fabric surfaces, it is the nanostructure of the surface that contributes to the evidently enhanced roughness and ensures that the wetting process falls into the Cassie-Baxter state. To be more exact, it has a disconnected contact line as shown in the image on the right side of the slide. Because of this structure, not only are the superhydrophobic properties improved, but also the contact angle hysteresis can be reduced and the delta theta gets close to 0. Let's take a closer look at fire retardant coatings. And in many work environments, textiles are subjected to extremely high temperatures or even exposed flames, producing demand for flame retardant textiles. Recently, ALD has been used to develop nanoscale thick fiber coating capable of resisting these extreme conditions. An example of these fire-resistant coatings can be seen in the photo to your right. The top image is of untreated cloth fibers, while the middle and bottom are images of cloth fibers being treated with 2 different chemicals, all at the same magnification of 15,000 times. Let's take a closer look at the nanocoatings. To test the flammability of the textiles, samples are typically subjected to the vertical flame test, where an open flame is placed at the base of a fabric sample, like those seen in the chart below. Here, a direct flame is applied for 12 seconds, and the results are then recorded. From this data, it can be seen that as the weight percent of the flame retardant surface coating is increased, so too does the fabric's resistance to combustion, even to the point where the material can self-extinguish. This is because the increased layer thickness provides non-flammable or flame-resistant materials to the surface, making it difficult for oxygen to reach the combustible fabric. This therefore increases the amount of oxygen in the environment needed for combustion to occur. If this required amount is much larger than that available, then the fabric will self-extinguish itself, like the samples in the table below. ALD's performance in textile coating compared to padding is very good. It has the ability to produce nanoscale coatings on complex geometry and can coat deep pits of the fibrous structure while having reduced heating times compared to other processes. However, this process is not one typically used by the industry, whereas padding is. This is because ALD is an expensive process, production of these materials is slow, and batch sizes are small. Additionally, many consumer products do not require nanoscale layering, and other processes, typically padding, is more commonly used. In this presentation, we covered the desired properties of surface modification of textiles and how they are achieved. We analyzed atomic layer deposition in two applications: hydrophobic and fire retardant coatings, as well as its comparison to padding. Surface modifications allow textiles to provide more safety and convenience in the modern world. After listening to this presentation, you should be able to answer each of the following questions. What are the advantages of atomic layer distribution or deposition over padding? Describe the 4 steps of atomic layer deposition. How does the thickness of an atomic layer deposition affect flame resistance? Thank you for listening.